Based on some stuff that came up last week in the online session, I decided to make a video just going over experimental design review. Obviously, we've done a lot of labs this year, so nothing here should be completely new. We've touched on all of this stuff a bunch. I just wanted to put it all in one place because I know that it is going to be a significant part of the AP exam this year based on what information they've released to me, as well as I'm sure you guys noticed that this kind of stuff is present. That's Yamasaki just never leaves me alone, ever. No school, still texting me all the time. Anyway, I'm sure in the practice problems you've noticed that these things have come up as well. So I just want to go over, some terms that you guys are probably going to see on the exam. Hypotheses, right? Null and alternative. We've never hung a name on alternative. Yamasaki, stop. I've never hung a name on alternative hypotheses, but we've definitely talked about them. Variables, independent, dependent, you guys should have those cold by now, but we'll briefly go through. And then controls, positive versus negative. There was some confusion, so I wanted to go over that. Okay, so hypotheses. Two types. Null, which you've seen before, and alternative, which you've seen before, but we haven't really gone over it specifically. So the null hypothesis is just a fancy way of saying nothing is happening. Any deviation from the normal or expected condition is due to random chance. This really factors in with chi-square analysis, where your null hypothesis is the expected is what I expect to see, and that's what's going on. So in Hardy-Weinberg equilibrium is an example of a null hypothesis. Like the population is in Hardy-Weinberg equilibrium means the population is not evolving, allele frequencies are not changing. Nothing is happening. Any deviation from the normal condition is due to random chance. With gene linkage, we did it this semester. We guys did a chi-square analysis on the Jackalope lab. And your null hypothesis was nothing funny is going on. Independent assortment is occurring. And of course, in that lab, you rejected your null hypothesis because the two genes that you were looking at, the two traits that you were looking at, were on the same chromosome. So there was a non-random cause of the difference from the expected. And that kind of leads us into alternative hypothesis. So alternative hypothesis is just the opposite of the null. Something is happening. There is a non-random cause of deviation from the normal expected condition. So when you do a chi-square analysis and you reject the null hypothesis, you're basically providing support for this alternative hypothesis, which in Hardy-Weinberg would be like natural selection or gene flow or genetic drift or sexual selection. Something is happening that is going to change the allele frequency. And then in gene linkage, it just means, okay, the genes are linked. They're on the same chromosome, whatever. Independent assortment is not the cause of the phenotypic frequencies in the F1 or F2 generations. Okay, variables, you guys should have this cold. Independent, the variable that the experimenters change or that you change when you're doing the experiment. Brine Shrimp Lab, salinity, temperature for the cellular respiration lab, amount of substrate for the enzyme lab. Anytime you guys designed your own experiment, it was the independent variable that I was allowing you to select, right? And then the dependent variable was the variable that was measured. So examples from class is the independent was the salinity of the brine of the solution, and your dependent was the number of viable hatchlings, from the first week of school. Cellular respiration lab, right? You were calculating the moles of oxygen consumed. And then the enzyme lab was kind of the reverse. You were looking at the moles of O2 produced by the yeast when you were adding the enzyme to the hydrogen peroxide, seeing how fast it catalyzed that reaction. Okay, last thing, controls, positive versus negative. So a negative control is a group where the dependent variable is not expected to be produced. Like you're not expecting a result to happen. usually because the independent variable isn't there, right? Like, for example, from the FRQ last week when they were talking about amanitin and, oh, actually, never mind. Um, I'm trying to think of it. Well, a negative control is just going to be like, for example, in the cellular respiration lab, the plastic beads, right? Something that doesn't respirate, so wouldn't be expected to consume oxygen, right? The independent variable that would produce a result isn't there, right? You would expect sort of no results. It's a way to sort of monitor any environmental factors that might be at play. Um, which contrasts with this positive control is a group where the dependent variable is expected to be produced normally, and the independent variable would inhibit or decrease the production of the dependent variable. So what I was thinking before, with the FRQ from this past week, the one where it was talking about amanitin and how it affects the uh, rate of transcription, um, of like that RNA, how it affects the activity of the RNA polymerase. The control that was missing that you had to talk about what it was, that was a positive control. It wasn't asking you that specifically, but it was a positive control because that would have been the rate of activity of this RNA polymerase in normal conditions when that amanitin wasn't present, because amanitin was expected to have an inhibitory effect on the RNA polymerase. So having the control there, that's what we call a positive control. Another example is if you were testing peas in the cellular respiration lab. If you had a neutral pH, something where you would expect them to do quite well, and you wouldn't expect pH of 7 to inhibit it, but then you wanted to see, okay, what happens in a pH of 4 or 3 or 9. If you wanted to deviate from that condition, you would have your positive control, because then you could look at your results through the lens of, well, okay, how does this relate to the normal situation? Like, how severely do these conditions inhibit the activity of my experiment? How does the variable that I am using in my experimental group, how does it inhibit my dependent variable, based on comparison with the positive control? Okay, so I hope that clears things up. Man, Yamasaki and Wise are just going crazy here on this text thread, so I should probably look at that. Okay, so hopefully that clears things up. I've just posted the Unit 2 FRQ for this week, but you can always refer back to this at any time if you need more clarification about experimental design. Okay, thanks.